Hello, calculus students, and welcome to an online lesson. Today we're going to be talking about discrete and continuous random variables and something known as probability distributions. The next few chapters will all be focusing on this word distribution. So we're starting a whole new unit here. And I guess without further ado, let's jump right in. So some terms of notation. I open off by saying, in this unit, we will focus on symbolic representations of concepts we learned in previous units on statistics and probability. So we're going to combine some of the things that we've seen, like variables we're talking about here, and that was part of our statistics unit. Continuous, discrete, again, all part of our our statistics unit. And we'll also be talking about probabilities and things like that. So it sort of bridges together those basic units that we had in the past and puts them together in this new way. Something known as a random variable. A random variable represents all possible outcomes which could occur for some random experiment. And that definition, I feel, is totally useless without some context. So let's start off by saying when we talk about a discrete random variable or a random variable, we use a capital variable, usually capital X, not lowercase x. And that's the variable. Now, if you go back to our statistics unit, what was a variable? A variable was not a number. A variable was like a label. A variable could be the colors of cars in the parking lot. The variable could be the number of students in Mr. Peacock's math studies class, which again, all these answers could change based on when you go and look. So when you see big X, capital X, think of a variable. And when you think of a variable, think of a label. So this is words. Big X is words. And then the possible values are little x's or data, numbers, values. So here's an example. The number of houses in your suburb which have a power safety switch. So depending on which suburb we're talking about, that could be 15 houses, that could be 20 houses, that could be 0 houses. All those numbers that I just read off, those are little x's. Those are data values. The actual label, which is the number of houses in your suburb which have a power safety switch, is big X. Moving on, the number of new bicycles sold each year by a bicycle store. Well, depending on which store we're talking about, that could be a different amount of bicycles. It could be 100 at one store, 50 at another, 150 somewhere else. The number of new bicycles sold each year, this wording is big X. Those values that I read off of 150, 150, those are data values, also known as little x. And so on and so forth. So the last example, the number of defective light bulbs in the purchase order of a city store. So each order could have a different number of defective light bulbs. The actual values would be little x, and this label here, this wording, this variable is big X. When we say discrete, those are counting values, just like they were in the statistics chapter. So number of houses, that's a counter. Count houses, you can't have half a house. Number of new bicycles, again, we're talking about whole bikes sold. Number of defective light bulbs, actual light bulbs. Continuous, these are talking about measurements. Once again, big X refers to the label, little x refers to the actual numbers. So an example of a big X would be the heights of men, or the volume of water in a rainwater tank during a given month. So heights of men, those are, again, that's our big X. The actual values of those heights, which would range in this interval according to this problem, those would be our little x. Volume of water in a rainwater tank in a given month, again, that's our big X, and the actual values would be little x. We can use this notation to make more complicated or complex mathematical statements. For example, I could say the probability that x equals 3 would be written this way. The probability big X equals 3. Now, big X could mean, again, the number of defective light bulbs in an order. So when I see this, knowing what big X is, I could say the probability that the number of defective light switches in an order equals 3, or is 3. All of that is given here. So if you define big X ahead of time, using this notation helps you to not have to rewrite your label over and over. You define what big X is, And then you can write these little statements. And then I've got a bunch of examples here, and you're welcome to read through those. I'll pull out another one at random. The probability that big X is at least 3. Again, I could write the probability, parentheses, big X greater than or equal to 3. And then we can do inequality intervals as well. The probability X is at least 3 but less than 7, or another way to say that is in between 3 and 7. In this example, a supermarket has 3 checkout points, A, B, and C. The government inspector checks the weighing scales for accuracy at each checkout. If a weighing scale is accurate, a Y is recorded, and if it's not, N is recorded. Suppose a random variable X is the number of accurate weighing scales at the supermarket. So that's what X represents. List the possible outcomes. All right, so I go through. When we take our fruit or produce to a checkout, they put it on the little scanner, which has a scale built in, and then they charge us. Obviously, we want to make sure those scales are accurate. So they come in, they take a weight that they're already familiar with, they check the scale. What could we have for A, B, and C? I'm going to make a little table off here to the right. So A, B, and C. I could have all of them working. I could have absolutely none of them working. I could have the first one and the other 2 not working. I could have just the second one working. I could have just the last one working. What else could I have? I could have the first 2 working. I could have the last 2 working. Or I could have the first and the last 2 working. And again, then we have none of them working at all. And those are all of our combinations. There might have been a better way to do that, but that's what we've got. So I'm looking at 8 different combinations here. It says list the possible outcomes. Done. Describe using X the events. Now we could have done that with a tree diagram as well. We could have said for the first one it's either yes or no, the next one yes or no, and then for that third one yes or no, and then you see again we get 8 different options. So I kind of already knew the answer was going to be 8 different outcomes, which we've listed. Describe using X the events of there being one accurate scale. Well, that would mean that X, again, which we represent here, the number of accurate weighing scales, so X is 1. That's really all they're asking us for here. Describe using X the events of there being. So that would be X equals 1. If I want to know the probability of that occurring, I would simply put a P in front of that. So that's the probability that big X equals 1. And again, big X is the number of accurate weighing scales at the supermarket. So I would read this whole statement as the probability that the number of accurate weighing scales at the supermarket equals 1. And we know that there was 1, 2, 3 ways to have 1. So that's 3 out of 8. So 3/8 would be our probability there. At least one accurate scale. Well, again, we're using big X again to represent our number of accurate weighing scales. Is at least 1, so it's greater than or equal to 1. Again, if we wanted to make that a probability, we could do it this way. Greater than or equal to 1. Well, that would be everything except for our last option. So that would be 7/8. For any random variable, there is a probability distribution. So this is the second part of our learning intention. Probability distribution. This provides us with all the possibilities of the variable and the probability of each occurring. Okay, so 2 things. Provides us with all the possibilities of the variable. So anything that your label could be. Could you have a possible answer of 0 or 1 or 2 or 3? It lists them all out, and then it also lists along with those some number between 0 and 1 that represents the probability of it occurring. A probability distribution can be displayed with a table, graph, or function. And the sum of probabilities in a probability distribution must equal 1. That's everything all put together. That is super important. Maybe the most important thing on this slide, and we'll see it reiterated in the remaining problems that we'll look at. A magazine store. Perhaps a thing of the past, but a magazine store recorded the number of magazines purchased by its customers in one day. 23% purchased 1 magazine, 38% purchased 2, 21% purchased 3, 13% purchased 4, and 5% purchased 5. What is the random variable? Again, the random variable is the descriptor. It is words. It is big X. And in this case, big X is the number of magazines purchased by its customers in one day. The number of magazines purchased by its customers in one day. Make a random variable probability table. So for our probability table, we are going to list two things. We are going to list, I'm going to do a horizontal table. That's how you usually see them. And I am going to say the probability, nope, let's try this again. We're going to have X, and we're going to have the probability that big X equals little x. Seems crazy, I know, but that's what we do. What does little x represent again? Little x is our actual number. What could our customers purchase? They could purchase 1, 2, 3, 4, or 5. 2, 3, 4, or 5. Those are all the different values of our random variable. They could be 1, 2, 3, or 4, or 5. Why can't it be 0? Because you're not a customer if you don't buy anything. Now, what does this statement here mean? This says the probability that the number of magazines purchased by a customer in one day is little x. So for this first one, I'm now writing down the probability that the number of magazines purchased by its customers in one day is 1. And what is the probability? Well, we have 23%. That's a probability, so I'll write 0.23. That's the probability that the number of magazines purchased by its customers in a day equals the data of, in this case, 1. Now, what about when big X equals 2? Well, that will be 0.38, we see, and then 0.21, and 0.13, and 0.5. Sorry, 0.05. Sorry about that. So, if we did this correctly, what should we know about all of these probabilities? They should add up to 1. So I have 23 plus 38, which gets me up to 61, plus 21 gets me up to 82, plus 13, which gets me to 95, and then 5 more, 100%, or 1 whole. Graph probability distribution. They won't ask you to do this very often, but it's basically X versus Y. X being our data, it's discrete, so we don't need to have a histogram. They don't need to be touching our graphs. So I'm just going to have 1 here, 2 here, 3 here, 4, and 5. And again, that would be, I could label this as my actual variable. I'm just going to save my time and call it big X for now. The number of magazines purchased by its customers in one day. And then my y is actually going to be probabilities, meaning that the highest value here should be 1, and I'm kind of out of room, so this would be 0.5 here, so on and so forth. And then I could make a little bar graph or column graph. So the first one has a probability of 0.23, so that would go up to about there. My second one has a probability of 0.38, goes to here. Actually, I didn't need to go all the way to 1 because we're not going any higher than that, so I could have adjusted my scale a little less here, though that looks more, I apologize. About half of that, and about half of that. And that would be an example of a graph of a probability distribution. What's it useful for? Well, right away I can see that the most likely occurrence is 2. That's the one that's most likely to occur or has the highest probability. The one that's least likely to occur would be 5 magazines purchased, and that has the smallest bar. So probability distributions, both via table, which would be the most common way, as well as via some graphs. Again, make sure that we know that all the probabilities add up to 1, the most useful thing from this lesson. So a die is rolled twice. Draw a grid which shows the sample space. We can do that. Oops. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And as I draw the grid, all my different outcomes will be where this black line intersects with my green line. So all these points here represent my sample space, which would be 36 different outcomes, so on and so forth. Suppose X denotes the sum of the dots in the uppermost die. Suppose X denotes the sum of the dots uppermost on the die for the two rolls, and find the probability distribution of X. So this is, what do the numbers add up to? When they say sum of the uppermost is just what you rolled as opposed to being on the side or on the bottom. What could we add up to? Well, the highest number that we can have is a 12. And the lowest number that we can have is a 2, right? 1 plus 1 will give us a 2. And then we can have everything in between there. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now, what's the probability that the sum of the uppermost numbers on the die, also known as big X, equals little x? So what's the probability that the sum is 2? Well, how many ways are there to get to? And that would just be this one right here. There's only one way to get to. So that's 1 out of 36. Now, what about getting a 3? Well, that would be this one or this one. And we see a little diagonal pattern going on here. So there's multiple ways to get a 3, a 1 and a 2, or a 2 and a 1. So that's 2 out of 36. How about a 4? Well, I could get a 3 and a 1, a 2 and a 2, or a 1 and a 3. And again, we see the diagonal going on, so that's 3 out of 36. And then for 4, I could have, for 5, I could have 4 and 1, 3 and 2, 2 and 3, or 1 and 4. So that gives me 4 out of 36. Nice pattern happening. And then to get a 6, I could have a, oops, I didn't draw one of my lines. I could have a 5 and a 1, 4 and a 2, 3 and a 3, 2 and a 4, or a 1 and a 5, which gives me 5 out of 36. For a 7, I could get a 6 and a 1, 5, 2, 3, 4, 4, 3, so on and so forth, which gets me 6 different values out of 36. And then we'll start to see the pattern get smaller each time. Now we're down to 5 on the next one, so 5 out of 36. And then it becomes 4 out of 36, 3 out of 36, 2. Whoops, something went terribly wrong. I apologize. What did I do wrong? Let me backtrack here for a second. Haste makes waste, folks. So I know there's only, oh, I'm sorry, everything was right. I was thinking that there were 2 dice that would make a 12, but only one combination of those 2. So everything's good here. So 2 out of 36, and then again, there's only one way to get a 12. That's 2 6s. So here's my probability distribution. Again, I should be able to add these up, and it should add up to 36. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 gives me 36 out of 36 is 1 whole. Now draw a probability distribution. It says histogram. I would argue that it shouldn't say histogram. It should just say column graph. Very quickly, what we would do here is we would have all of our values. Again, 1, 2, 3, 4. I'm sorry, not 1, 2. Starting with 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. The highest value I ever need to get to is 636. So that would be 636, and then I would have 336, and then 2, 1, so on and so forth. So my first one just goes up to 1, and then goes up to 2, and then 3, and 4, and 5, and 6. And then it starts coming down. that would be my probability distribution bar graph for that. Again, you can see the most commonly rolled number is a 7, and that's why they say 7 is a lucky number. And then the least ones would be snake eyes over here, 2 1s or 2 6s, getting us a 12. All right, probability distribution represented with both a grid and with a bar graph. A few problems in the book on page 610 and 612. Again, from today's lesson, we should be able to explain why a random variable is discrete or continuous, again, knowing whether it's counted or measured, give possible values for that variable, like we did on our different problems here, and then use a probability distribution to successfully answer questions about that data's probability. Again, like we did when we looked at which one was the most commonly occurring and which one was the least commonly occurring, and also knowing that our probabilities should all add up to 1. Until next time.